What does learning look like? Maybe you'll come away from these talks and you'll tell your friends, I learned something today, as if you gained something that you didn't have before. Intuitively, learning feels like the acquisition of new information that we store inside our brains as memories. Maybe our eyes and ears are like imperfect cameras trying to capture the world around us and figure out what would be useful to play back later. Hi, everybody. My name is Zeeshan, and I've been fascinated with the inner workings of how we learn and how our brains create memories. But I have to tell you first, I've been at the final stretch of my PhD now, and as someone who's on the way to finish grade 25 of being in school, it's a daunting time to be a student. In an era where we wake up the next day and see headlines on how AI has reached PhD-level knowledge, it feels impossible to keep up. And we can't help but feel defeated when we spend hours trying to digest a research paper, only to forget half the details a week later. And meanwhile, ChatGPT can still summarize it almost perfectly every time you ask it to. That begs the question, what is going on in here? Why is learning so difficult? And why are our memories so fragile and unreliable? Well, an alternative idea is that maybe learning isn't about storing new experiences directly in the brain, but about creating them from what we already know. For example, maybe you're reading a book and you come across a new word, innocuous. You think, well, it kind of looks like the word innocent, but the root of the word, innocuous, that doesn't sound very pleasant, so maybe it means the opposite of unpleasant? You look up the definition and you see it means harmless. So your initial guesses weren't that far off. Now think about it. You just learned a new word, but did you really learn it from scratch? Innocuous. The sound isn't different to your ears, but it became meaningful to you after you attached it to other words and concepts that you knew about. In other words, you learned by taking a seemingly novel experience and matching it with something familiar. So which is it? Do we learn by experiencing the world and then storing those experiences as memories? Or do we learn by creating ideas from what we already know? I wanted to test this by teaching mice how to play video games. Specifically, I taught these mice an image location association task where they had to learn, through trial and error, that touching specific images in specific locations, for example, this spider image here on the right, would give them a tasty strawberry milk reward on the other side of the room. Now, mice had to learn 3 different image location associations across 6 different trial types. Seems pretty tricky, but believe it or not, mice can actually learn to do this pretty well. But it takes many thousands of trials across many weeks of training to get really good at it. Now, we can track how the animal moves in space with a camera and trace out their trajectories to try and figure out what kind of strategy they might be using to solve the task. And what we found was pretty interesting. The better the mice got at this task, the more structured and organized their behaviors were. For example, this mouse here always liked to turn in a counterclockwise direction and check the right side of the screen, and then the middle, and then the left, as if it was following a step-by-step process to figure out what to do, instead of just roaming around aimlessly. Now, you can imagine this is impressive, but it would be pretty hard to learn this completely from scratch. So in the same way you teach a mouse or you teach your pets a new trick, I taught these mice something simpler to get started. So first, I would just show a white square on the screen. All the mouse had to do was touch the white square, and it would get a reward. Pretty simple, right? Next, I made it so that the light would turn on right above the reward port. If the mice wanted the white square to show up on the screen, they first had to touch the reward port, and then the square would show up. Finally, I added a rule where the mice would have to only touch the white square on the screen. If they touched any other part of the touchscreen, they would get a timeout, and they would have to wait an extra long time before they would be allowed to try anything again. This last step taught the mice to be patient and to think out their actions a little more carefully instead of just walking around and touching everything. Now think about it. This training period is pretty important. Maybe if you have a tutor or a coach and you're struggling with something, they always tell you the same thing. Go back to the basics. It doesn't matter how good you are at something, if you don't have a strong foundation of the fundamentals, you're not going to get anywhere. So while this pre-training might seem trivial, it's key. It teaches the mice that their actions have consequences in shaping the world around them. Now, what I'm interested in as a neuroscientist is how does the brain interpret this new complicated task? Does it think of it as a completely new task? Or does it use what it learned from the much basic and easier pre-training tasks to figure out what to do? Well, first of all, how do we look at the brain? Traditionally, we use electrodes, which are thin wires that you insert into the brain to measure the activity of individual neurons. But the problem with doing that is we can't track the same neurons across many different weeks. We need something that's more like a camera. But the problem with using a camera is that neurons are very tiny, on the order of microns, so we need one that can also work like a microscope. In my experiments, I used a device called a microendoscope, and it works a lot like you might think it does. This is a miniaturized microscope that attaches magnetically onto the mouse's head and only weighs a couple grams. I surgically implant a very thin lens through the mouse's skull to create a tiny window into the mouse's brain, and then the microendoscope can image many hundreds of individual neurons and track them like a camera. So what do a bunch of active living neurons look like inside the brain? Well, we placed a lens deep inside the brain, targeting an area called the hippocampus, which is critical for learning and memory. You can see here many hundreds of individual neurons lighting up as the animal is doing the task. Now you might be wondering, how is it possible for all of these neurons to be lighting up this way? Well, when you think about electrical activity in the brain, it's really just charged ions moving in and out of the neurons. Neurons don't normally light up this way, but we genetically modified them so that they have sort of like a superpower where they will light up anytime they detect a change in their concentration of ions. And we use this light to estimate the level of activity. So, what does learning look like in the brain? Well, what we found is that the better the mice got at this task, the more neurons we found in their hippocampus that cared about the direction in which the mouse was moving. For example, some neurons would light up whenever the mouse would turn left, some would light up whenever it would turn right, and so on. Now, when you think about this, this kind of makes sense. Remember, these expert mice developed a strategy where they would often turn in a specific direction before deciding where to go. So having to remember the right trajectories to take to solve the task seems pretty important. But the big question here is, did these individual neurons learn to respond to these directions of movement, or were they already responding to them during the pre-training period? If we are to think that the brain interprets this new task as completely different from the earlier pre-training task, then it would be a new memory that it would have to learn from scratch. And that would mean that the directions in which the neurons respond to would be completely different. But that's not what we saw at all. If we looked at the neurons that cared the most about the directions in which the mouse was moving, we saw that they cared about those same directions even in the pre-training period, way before the animal had created any of those intricate movement patterns that I showed you earlier. The only thing that changed was how strongly they were responsive. Some became more strong in their responses and some less so. But they were always responsive to the same movement directions throughout the entire learning experience. Now, this is really interesting because it tells us that those basic actions that the mouse learned way earlier in the pre-training period were still fundamental for the brain to figure out how to do the task. All the brain had to do was sort of work like an equalizer. It would turn the volume up on some neurons, it would turn the volume down on others, and figure out in what order the neurons should activate to create a trajectory to solve the task. Now, this tells us that when we learn something, we're not creating a completely new pattern in the brain every single time. Rather, we're recombining concepts in our existing knowledge base to create new ideas. It's kind of like how a musician can create completely new melodies from the same sets of baseline notes. In other words, learning is compositional. It's a reflection of our ability to generate new ideas from what we already know. Take, for example, this very talk. No new words were uttered in this presentation. No new sounds that your ears couldn't make sense of, but you still learned something. Because it wasn't the words or the sounds that you were trying to learn, but the order in which they were sequenced that unlocked a pattern in your brain that you now find meaningful. So, in a way, our brains work a little bit like the generative AI models that we're hyping up these days. Both use existing concepts and recombine them in new ways. But the critical difference here is that the weights between the concepts in AI are like the average across the entirety of the internet. The problem with this is this leads to a very statistically consistent way about thinking about things. It's probably why you always get that generic, it's not this, it's that kind of response from ChatGPT all the time. True progress doesn't come from how much we know, but the diversity in the way we think. For example, I know many of the same neuroscience concepts as my fellow graduate students. But how I learn these concepts and how each of these concepts fit in differently to our existing knowledge bases, that is what determines the diversity of ideas that we're all able to come up with. Something that AI really can't rival yet. As a final thought, I'd like to say that, I've been a student for all my life, but I've also been a teacher. I made it a habit to try to teach in some capacity, whether it's swimming lessons or computational neuroscience, all throughout these years, and I've learned the same thing throughout. Every student is different, but every student is also capable. People learn best the better you get to know them, and the better you get to know the key words you need to use to unlock that aha moment that their unique brain finds meaningful. Because nothing is ever completely unfamiliar to the brain. Everything is always like something else, and you have the capacity to learn anything you set your mind to. Thank you.